The final periodic trend that we're going to look at is the trend in ion size. And this will pair nicely with the trend in atomic size, or atomic radius. So ions of the main group elements will typically have filled outer shells, complete octets. You should know the common ions for the main group elements based on their electron configurations. That group 1 would like to lose 1 electron to achieve that noble gas configuration and have a positive charge. Group 2 elements will lose 2 electrons to achieve a filled outer shell. And then on the other side of the periodic table, we have elements in the halogen group gaining an electron to achieve noble gas configuration, the oxygen group gaining 2, nitrogen group gaining 3. And so I do expect you to recognize these common charges for those main group elements shown here. Now let's think about how the size of those ions will differ from the size of the neutral atoms. So as we remove an electron, say from the 2s or 3s orbital, in the case of a group 1 or 2 element, those ions get smaller. We're removing a shell, essentially. And so only my core electrons are left. And so cations will always be smaller than their parent atom. On the other hand, anions, negatively charged species, will always be larger than their parent ion because we're adding electrons to the shell. We're also going to look at the trends in ion size in an isoelectronic series. Isoelectronic means that the atoms or ions have the same electron configuration and therefore the same number of electrons. If we look at this grouping of elements from the periodic table from rows 2 and rows 3, these elements, these 6 elements, would all be isoelectronic. Aluminum has lost 3 electrons to have noble gas configuration of neon. Fluorine has gained 1 to be configuration of neon. Nitrogen has gained 3. So all of these will have electron configuration of neon. And we can throw that into our mix too. So all 7 of these elements have the same electron configuration. 10 valence electrons. 10 total electrons, rather. So the number of protons within each of these, we have 11, 12, 13, and this is 10, 9, 8, and 7. So the largest atoms are going to have the largest effective nuclear charge. And remember, our simple calculation for effective nuclear charge is equal to the atomic number minus the shielding constant, and this is the number of core electrons. So, for example, nitrogen would have 7 protons, so 7 minus the core electrons would be 2, so it would have an effective nuclear charge of 5 for nitrogen. Aluminum, on the other hand, will have 13 protons minus its core electrons, which, since it has 10 electrons now, the core electrons are going to be the same 2 from the 1s orbital, so my effective nuclear charge is 11, much larger. So we have our ends of the spectrum. Aluminum 3+ is going to be the smallest, it has the largest effective nuclear charge, and nitrogen 3- will be the largest one. It has the smallest effective nuclear charge. We can also look at this in terms of charges, right? We know that the cations are all going to be smaller than the anions, and the neutral atom will fall right in the middle. And the magnitude of charge is also important. So the higher the magnitude of charge, when it's positive, we're going to have smaller atoms. The higher magnitude of charge when it's negative, we're going to have larger atoms. So we can place this in order as such. And so this is the trend in size from smallest to largest for an isoelectronic series where all of these atoms or ions have the same electron configuration. Thanks for watching.